Module 19, Lecture B, Semi-supervised. By the end of this lecture, you will be able to represent labeled and unlabeled samples for semi-supervised estimators, apply self-training with threshold and k-best pseudo-labeling strategies, and use graph-based label propagation and spreading methods and evaluate their behavior. Semi-supervised setup. Unlabeled sample encoding. Semi-supervised learning uses both labeled and unlabeled data, so the model must clearly distinguish known targets from unknown ones. All samples are usually stored together, while known targets keep their class labels, and unknown targets use a special placeholder, such as -1. This tells the algorithm which examples are reliable for training, while still allowing it to learn from the overall data structure. In semi-supervised learning, unlabeled samples should use a placeholder that cannot be mistaken for a real class label. For example, if the classes are 0 and 1, -1 can safely mark unlabeled data, while string labels may need conversion to match the estimator's requirements. Use the same marker for every unlabeled sample, and make sure no labeled sample uses it by mistake. In semi-supervised learning, unlabeled samples should use the same feature preprocessing as labeled samples, such as scaling or text vectorization, but their targets must be clearly marked as unlabeled. This lets the model use their input patterns, like clusters or neighborhoods, without treating them as confirmed class examples. For instance, untranscribed speech can still reveal useful information about accents and background noise while preserving the reliability of the labeled data. Python code, unlabeled sample encoding. This example shows how unlabeled samples are represented in semi-supervised learning. Unknown labels are marked with -1, and the output summarizes how many samples are labeled and unlabeled. We import NumPy and pandas for numerical work and data handling, then bring in the iris dataset loader from Scikit-Learn for a standard classification dataset. We also import Scikit-Learn to support machine learning tasks. Together, these imports prepare the environment for data analysis and model building. We load the classic iris classification dataset from Scikit-Learn and use a small subset for a semi-supervised learning example. Specifically, we take the first 12 samples, keeping only sepal length and sepal width, along with their true class labels. This gives us a simple, manageable dataset for demonstration. To prepare data for semi-supervised learning, the true labels are first copied, so the original labels remain unchanged. Some selected samples are then marked as unlabeled by assigning them a special value of -1. This creates a label set that mixes known labels with unlabeled samples for training. First, identify the unique true class labels in the dataset. Then check whether the unlabeled marker, -1, appears among those real labels. If it does, raise an error, because the marker for unknown labels must be separate from any actual class label. We create a status array that marks each sample as labeled or unlabeled. A NumPy selection checks whether each label matches the unlabeled marker, then assigns the appropriate status. This makes it easy to separate samples with known labels from those without them. A pandas data frame is used to organize the semi-supervised dataset in a clear structure. It includes sepal length and sepal width as features, along with a target value that stores either the class label or an unlabeled marker. A status field then identifies each sample as labeled or unlabeled, making it easier to inspect the data distribution. Count the labeled samples by checking which entries in the semi-supervised labels are not the unlabeled marker, and count the unlabeled samples by checking which entries match that marker. Convert both counts to integers so they are ready for later processing or display. The output summarizes key dataset and setup details for a semi-supervised learning example. It reports the Scikit-Learn version for reproducibility, identifies -1 as the marker for unlabeled samples, and shows the dataset's real class labels. It also compares how many samples are labeled versus unlabeled, then previews the first 5 rows to show the data structure and label status. This script shows how to mark unlabeled data for semi-supervised learning using a small subset of the iris dataset. It keeps 2 features from the first 12 samples, copies the true labels, and marks selected samples as unlabeled with -1, while confirming that this marker is not an actual class. It then summarizes the labeled and unlabeled counts and displays a preview of the data, showing how the encoding separates known labels from unlabeled samples. Self-training basics. Self-training is a semi-supervised method that uses a small labeled dataset together with a larger unlabeled one. A model is first trained on the labeled data. Then it assigns labels to unlabeled examples, keeping only the most confident predictions as pseudo-labels. These pseudo-labeled examples are added to the training data, while still being distinguished from human-labeled data, helping the model improve by learning from both sources. A classifier can use a small labeled dataset to begin learning, then assign pseudo-labels to unlabeled examples when it is confident in its predictions. Those high-confidence examples are added to later training rounds, helping the model improve when labeled data is limited. This semi-supervised approach is useful in areas like medical imaging and document classification, where raw data is abundant, but labels are scarce. Self-training can improve a model, but it must be controlled to avoid reinforcing wrong pseudo-labels. Confidence thresholds or limits on accepted predictions help reduce this risk. In a good workflow, labeled data remains the most trusted source. Unlabeled data provides room to expand, and pseudo-labeled data supports training without changing the dataset's basic structure. Python code. Self-training basics. This example shows how self-training marks unlabeled samples, using -1 for unlabeled targets in Scikit-Learn. The result compares the original trusted labels with the pseudo-labels assigned during training. This setup imports key tools for a semi-supervised classification example. NumPy supports numerical work, while Scikit-Learn provides the iris dataset, logistic regression for supervised classification, and a self-training classifier. The self-training approach uses a small labeled dataset to help assign labels to unlabeled data, improving the model through repeated predictions. We load the classic iris classification dataset from Scikit-Learn. It provides flower measurements as input features and the matching species labels as the true targets, giving us the data needed to train and evaluate a machine learning model. A semi-supervised label set is created by marking every sample as unlabeled at first. Then, for each class, only the first 5 samples are given their true class label. This leaves a small trusted labeled set for each class, while the remaining samples stay unlabeled for self-training. The process counts how many samples have trusted labels and how many are unlabeled, using -1 to mark unlabeled entries. If either group is missing, it raises an error because self-training requires both labeled and unlabeled samples to run. A logistic regression model is used as the base learner, with a fixed random state for reproducibility and enough iterations to support training. It is then placed inside a self-training classifier that labels unlabeled samples only when its confidence is at least 80%. This threshold-based approach lets the model gradually learn from high-confidence pseudo-labels and improve over time. A self-training classifier is trained on the dataset using semi-supervised labels, where -1 marks unlabeled samples. After training, we count how many originally unlabeled samples received pseudo-labels from the model. We then measure performance by comparing the model's predictions with the true labels to calculate its accuracy. The code reports key details from a self-training experiment: the Scikit-Learn version, the number of trusted labeled samples, and the number of initially unlabeled samples. It then shows how many unlabeled samples received pseudo-labels, and reports the model's accuracy against the true labels, rounded to 3 decimal places. This script shows self-training on the iris dataset by starting with a small set of trusted labels and treating the remaining samples as unlabeled. A logistic regression model inside a self-training classifier assigns pseudo-labels only when its confidence reaches 80%. The output compares the number of human-labeled, unlabeled, and pseudo-labeled samples, then reports accuracy against the true labels to show how well the method worked. It also prints the Scikit-Learn version for reference. Choosing base estimators. In semi-supervised learning, the base estimator is important because it uses a small amount of labeled data to guide learning from many unlabeled samples. The labeled data links inputs to classes, while the unlabeled data shows the broader structure of the input space. A strong estimator should form reliable decision boundaries with limited supervision and make cautious, confident predictions, especially in settings like medical imaging or customer feedback analysis. In semi-supervised learning, the base estimator must provide reliable confidence measures, such as probabilities or decision scores, not just class predictions. These scores help choose which unlabeled examples are safe to pseudo-label. Because wrong pseudo-labels can spread and harm later predictions, the estimator should be accurate, well-calibrated, and robust when data is ambiguous. Choose a base estimator that fits your data, labeled examples, and problem assumptions. Linear models suit simpler features, tree-based models capture complex interactions, and neural networks can handle inputs like images or audio but need regularization. In semi-supervised learning, first validate the estimator on labeled data, because its predictions may become new training examples. So balance accuracy, confidence, cost, and interpretability. Python code. Choosing base estimators. This example compares different base estimators used for self-training. Unlabeled samples are marked with a target label of -1, and the quality of each model's confidence determines which pseudo-labels are accepted. This setup imports NumPy for numerical work and Scikit-Learn tools for machine learning. It includes a synthetic classification data generator, logistic regression for probability-based classification, a self-training classifier for semi-supervised learning, and a decision tree classifier as another possible base model. We create a reproducible synthetic classification dataset with Scikit-Learn's make classification function. It contains 300 samples with 2 informative features, no redundant features, and 1 cluster per class. A class separation value of 1.2 makes the classes reasonably distinct. We create a label array matching the true labels, but initially mark every sample as unlabeled. Then we choose 2 small ranges of sample positions to label and copy their true labels into the new array. This leaves only those selected samples labeled, while all others remain unlabeled. We first verify that the semi-supervised dataset contains the expected number of labeled samples. Unlabeled entries are marked as -1, so we count the labels that are not -1 and require the total to be exactly 20. If the count is different, an error is raised to prevent training with an incorrectly prepared dataset. A set of base estimators is created with 2 models, logistic regression and a decision tree classifier. Both use a fixed random state for consistent results, while logistic regression is given enough iterations to converge, and the decision tree is limited to a depth of 3. These models are chosen because they can produce probability estimates, which are needed for the later self-training process. The code first prints the Scikit-Learn version to support compatibility and reproducibility. It then counts how many samples have known labels and how many are unlabeled, using -1 to identify unlabeled entries. Together, these outputs give a quick summary of the dataset's labeling status. For each base estimator, a self-training classifier is built with a pseudo-label threshold of 0.85 and up to 10 iterations. The model is trained on the features and semi-supervised labels, then evaluated by counting accepted samples and measuring accuracy against the true labels. The results report each estimator's name, accepted sample count, and accuracy rounded to 3 decimal places. This script shows self-training for semi-supervised learning using logistic regression and a shallow decision tree. It creates a small synthetic dataset where only 20 of 300 samples are labeled, then trains each model to add pseudo-labels only when predictions are confident enough. Finally, it reports how many unlabeled samples each model accepted and its accuracy, showing that different base classifiers can produce different pseudo-labeling behavior and performance. Pseudo-labeling strategies, confidence thresholds. Confidence thresholds in self-training decide which unlabeled examples are reliable enough to receive pseudo-labels. A model first predicts labels for unlabeled data, then keeps only predictions with high confidence for further training. This reduces noise by using clear, familiar cases while leaving ambiguous examples for later, such as labeling a clear dog image but not a blurry one. In self-training, the confidence threshold controls which predictions become pseudo-labels. Confidence thresholds are useful, but a model's confidence may not reflect its true accuracy, especially when it is poorly calibrated or the data environment changes. To reduce misleading pseudo-labels, pair thresholds with validation checks and retrain gradually. Different classes may also need different thresholds, since one shared cutoff can favor easier classes and create imbalance. Effective thresholding depends on understanding model uncertainty and the training impact of incorrect labels. Python code, confidence thresholds. In self-training, confidence thresholds control which pseudo-labels are accepted for further learning. A strict threshold keeps only the most confident predictions, while a relaxed threshold allows more examples but may include less reliable labels. Changing the threshold directly changes how many examples are accepted and how selective the training process becomes. We import NumPy for numerical work and Scikit-Learn for machine learning tools. From Scikit-Learn, we use utilities to create a synthetic classification dataset, split it into training and testing sets, train a logistic regression model, and measure prediction accuracy. We also import a self-training classifier, which supports semi-supervised learning by using both labeled and unlabeled data. We create a synthetic classification dataset using Scikit-Learn's make classification function to test a model in a controlled setting. The dataset has 600 samples, 6 features, and 3 classes, with 4 features carrying useful information for predicting the target. A fixed random state makes the results reproducible. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 35% of the data is kept for testing, giving us a separate set to evaluate the model. Stratifying by the labels preserves the class balance in both sets, and setting a random state makes the split reproducible. First, a fixed random seed is set, so the results are reproducible. Then, a label array matching the training labels is created and filled with -1s to mark most examples as unlabeled. This simulates a semi-supervised setting where only a small portion of the training data has known labels. To create a semi-supervised setup, the process selects a small number of labeled examples from each class. It finds all training samples for a class, randomly chooses 12 of them without replacement, and keeps their true labels. All other samples remain unlabeled, so the dataset has only a few labeled examples per class. We count labeled samples by finding entries whose semi-label is not -1, and unlabeled samples by finding entries whose semi-label is -1. Confirming both counts ensures the dataset contains the labeled and unlabeled data needed for self-training. The code verifies that the training data includes both labeled and unlabeled samples. If either group is missing, it raises an error. This check is necessary because self-training and semi-supervised learning depends on having both types of data. We set two confidence thresholds, 0.75 and 0.95, to control when the model accepts pseudo-labels during self-training. We also prepare a results record to track each threshold, how many pseudo-labels are accepted, and the final test accuracy. This lets us compare how different confidence levels affect model performance. For each threshold value, a logistic regression model is created, with fixed settings for reproducibility, then used as the base model in a self-training classifier. The classifier accepts pseudo-labels according to the current threshold, and is trained on the feature data with semi-supervised labels, allowing it to learn from both labeled and unlabeled examples. The process measures how many pseudo-labels the self-training classifier accepted by comparing assigned labels with the original labeled set. It then uses the trained classifier to predict the test labels and evaluates accuracy against the true labels. The threshold, accepted pseudo-label count, and test accuracy are saved for later analysis. The output first shows the Scikit-Learn version to support compatibility and reproducibility. It then reports how many training samples were labeled at the start and how many were unlabeled, giving context for the amount of true information available and the scale of labels the self-training model needed to infer. The code summarizes each result by reporting the confidence threshold, the number of accepted pseudo-labels, and the resulting test accuracy. This makes it easy to compare how different thresholds affect both model performance and how many pseudo-labels are used. This script shows how confidence thresholds affect pseudo-labeling in a self-training logistic regression model. It uses a three-class synthetic dataset where most training labels are hidden, then compares thresholds of 0.75 and 0.95. The lower threshold accepts more pseudo-labels, which can provide more training data but may add noise, while the higher threshold accepts fewer labels that may be more reliable. The output reports how many pseudo-labels were accepted and the test accuracy for each threshold. K-best pseudo-labels. K-best pseudo-labeling is a self-training approach that adds only the model's most confident predictions from unlabeled data back into training. By choosing just a small set each round, the model learns gradually and avoids relying on uncertain labels. This is useful when confidence scores are hard to compare across classes or training stages, such as in medical image classification. The K-best strategy depends on choosing the right number of pseudo-labels. Too few slows learning, while too many can add noisy errors and hurt performance. A better approach is to start with a small set of highly confident labels and increase the number as the model becomes more stable. This lets the model use unlabeled data effectively while limiting the risk of noise. K-best pseudo-labeling controls how quickly unlabeled data enters training, but it must be monitored carefully. The model may choose only familiar, easy examples and overlook more diverse or difficult cases. Combining it with class balancing or diversity checks helps improve coverage and overall performance while expanding the labeled dataset at a steady pace. Python code, K-best pseudo-labels. This section demonstrates K-best pseudo-labeling, where only the most confident model predictions are added as new training labels. It highlights how this selective approach supports self-training while reducing the risk of adding unreliable labels. It also compares cautious self-training, which adds fewer high-confidence predictions, with aggressive self-training, which adds more predictions but may introduce more errors. We import NumPy for efficient numerical work and use Scikit-Learn for the main machine learning steps. From Scikit-Learn, we bring in tools to create a synthetic classification dataset, build a logistic regression model, split the data into training and testing sets, measure prediction accuracy, and standardize features. Together, these imports support a basic workflow for preparing data, training a binary classifier, and evaluating it on unseen data. We create a synthetic binary classification dataset using Scikit-Learn's make classification function. It contains 600 samples with 6 features, 4 of which are informative for predicting the target. A fixed random state ensures the results are reproducible, giving us a controlled dataset for testing pseudo-labeling. We split the dataset into training and testing sets, so the model is evaluated on data it has not seen during training. Using Scikit-Learn's train-test split function, 35% of the data is reserved for testing and 65% for training. Stratifying by the labels keeps the class balance consistent in both sets, and setting a random state makes the split reproducible. A standard scaler is used to put features on a common scale by centering them and adjusting their spread. It is fitted only on the training data, then used to transform both the training and test data. This keeps the scaling consistent and helps many machine learning algorithms perform better. A fixed random seed is used so the selection can be reproduced. For each class in the training labels, 8 matching examples are chosen at random without replacement. These indices are collected as the labeled set, giving each class equal representation while leaving the remaining labels hidden. The code organizes the labeled data indices, then creates a complete set of training indices. It identifies the unlabeled data by subtracting the labeled indices from the full training set. This separation supports pseudo-labeling by making it clear which data points are still unlabeled and available for confident predictions to be added later. The code verifies that the pseudo-labeling setup is valid by requiring exactly 16 labeled examples and at least 1 unlabeled example. If these conditions are not met, it raises an error to stop the process before continuing. The function initializes self-training by making working copies of the labeled and unlabeled data indices, so the originals stay unchanged. It also copies the training labels into a separate set of labels that can be updated during training. As pseudo-labels are added, the model can learn from both the original labeled data and the newly labeled examples. The loop repeats for a set number of rounds, training the logistic regression model each time with a fixed random state for consistent results. In each round, the model learns from the currently labeled data and its pseudo-labels, using the most confident predictions to improve classification of the remaining unlabeled data. The model estimates class probabilities for each unlabeled training sample, showing how confident it is in each possible prediction. For each sample, the highest probability becomes the confidence score, and the matching class becomes the predicted label. These confidence scores help choose the most reliable predictions for pseudo-labeling. In each round, we add only as many pseudo-labels as allowed, without exceeding the number of unlabeled samples available. We then rank the model's predictions by confidence and choose the most confident ones. These selected samples are used to expand the labeled dataset. The code adds only the most confident predicted labels as new pseudo-labels, helping keep the training data reliable. It then expands the labeled set with these selected examples and removes them from the unlabeled set, so they are not chosen again in later pseudo-labeling rounds. A logistic regression model is created with a fixed random state for reproducibility and a higher iteration limit to support training. It is trained on the current labeled data, using the available features and pseudo-labels, then used to predict labels for the test data. The code evaluates the model by comparing its predicted test labels with the true labels to calculate accuracy. It also counts how many pseudo-labels were added during self-training, by comparing the current labeled data size with the original size. Together, these results show both model performance and the impact of the pseudo-labeling strategy. A logistic regression model is trained on the initially labeled data using fixed settings for reproducibility. Its predictions on the test set are then evaluated with an accuracy score. This result provides a baseline for comparing the later pseudo-labeling approach. To study how the choice of K affects pseudo-labeling, we run self-training for 6 rounds with a cautious setting of 5, then with a more aggressive setting of 30. For each run, we record the accuracy and how many pseudo-labels are added. Comparing the two results shows how quickly adding pseudo-labels can influence model performance. The output first confirms the Scikit-Learn version and the size of the original labeled dataset for reproducibility and context. It then compares the baseline accuracy from training only on labeled data with results after adding pseudo-labels. A cautious setting with K equals 5 shows the effect of adding a few confident predictions, while a more aggressive setting with K equals 30 shows how adding more pseudo-labels changes accuracy. This script shows self-training with pseudo-labeling using logistic regression. It begins with a small labeled portion of a synthetic dataset and treats the remaining training data as unlabeled. The model repeatedly adds its most confident predictions to the labeled set, comparing a cautious strategy that adds 5 pseudo-labels per round with a more aggressive strategy that adds 30. The results compare these approaches with a baseline trained only on the original labels, showing how pseudo-labeling can improve accuracy while balancing confidence against speed. Avoiding confirmation bias. In self-training, confirmation bias occurs when a model treats its own early predictions as reliable labels. This is especially risky in pseudo-labeling, where predicted labels from unlabeled data are added back into training and can reinforce initial mistakes. For example, a medical imaging model might learn a false link between scanner type and diagnosis. Pseudo-labels can be useful, but they should be treated as uncertain rather than absolute truth. Threshold-based and K-best pseudo-labeling must be used carefully to reduce confirmation bias without making it worse. High-confidence predictions are not always correct, especially with poorly calibrated models or varied data, and K-best selection can overemphasize easy or dominant classes. Practitioners should monitor label distribution and add pseudo-labels in a balanced way, so the model does not reinforce existing biases. To reduce confirmation bias in self-training, add pseudo-labels slowly and selectively, and monitor results with a reliable validation set. If performance drops, incorrect pseudo-labels may be harming the model. Keep human-labeled and pseudo-labeled data separate because they differ in reliability, and give pseudo-labels less influence or update them when predictions change. Choose pseudo-labels from diverse classes and sources so the model learns a broader, less biased view. Graph-based labeling, label propagation. Label propagation is a semi-supervised method that represents data as a graph, with samples as nodes and connections showing similarity. Starting from a small set of labeled samples, it spreads label information through the graph, so similar unlabeled samples can be classified. Its main strength is that it uses the structure of the whole dataset, not just the labeled examples, to guide predictions. Label propagation works best when the graph connects similar samples strongly, allowing labels to spread through clear clusters. It can be useful for tasks such as identifying user interests in dense social media communities. However, weak or misleading connections can limit accuracy or send labels to the wrong samples. The method is easy to interpret, but it depends on a high-quality similarity graph. In classical label propagation, labeled samples stay fixed while unlabeled samples update from nearby nodes. This can stabilize learning when labels are correct. but wrong anchor labels can spread errors, especially in central parts of the graph. Evaluation should consider not only accuracy, but also whether the graph supports meaningful label flow and where mistakes may cluster. The method is useful with large unlabeled datasets, such as in document classification or fraud detection, but it depends heavily on a well-built similarity graph. Python code. Label propagation. Label propagation uses a small set of labeled samples to infer labels for nearby unlabeled points through a graph. Points that are close to each other tend to share labels, and the result includes both the predicted labels and their confidence. This setup imports the main tools needed for a semi-supervised learning example. NumPy handles numerical arrays, Matplotlib creates visualizations, and Scikit-Learn provides machine learning utilities. From Scikit-Learn, synthetic clustered data is generated. Label propagation is used to spread labels from a small labeled set, and accuracy scoring evaluates the model's predictions against the true labels. We generate synthetic data with Scikit-Learn's makeBlobs function to create two clusters for semi-supervised classification. The dataset contains 160 samples, with a moderate cluster spread and a fixed random state for reproducible results. The function provides both the feature data and the true labels, which are later used to evaluate label propagation. We start by marking all training samples as unlabeled. Then, we set the first two samples to their true labels, giving the label propagation process a small set of known labels to begin from. Before label propagation, the two initial labeled samples are checked to make sure they come from different classes. If they have the same label, the process finds another sample with a different true label, clears the second seed's current label, and replaces it with that different class label. This ensures the starting seeds represent separate classes. We set up a label propagation model in Scikit-Learn using a k-nearest neighbors approach, where labels are spread based on the 10 closest data points. The model is allowed up to 1,000 iterations to converge. After fitting it to the feature data and initial labels, it uses both labeled and unlabeled samples to infer missing labels from the data's graph structure. After label propagation, we use the model's inferred labels for each data point as the predictions. We then compare these predictions with the true labels using Scikit-Learn's accuracy score, which shows the proportion of labels the model got correct. For each sample, confidence is measured by taking the highest probability in its predicted labeled distribution. The analysis then focuses on the originally unlabeled samples and averages their confidence scores. This average shows how certain the model is about the labels it inferred for the unlabeled data. The output reports key checks for a label propagation model: the Scikit-Learn version for reproducibility, the number of samples that were labeled at the start, and the model's accuracy against the true labels. It also shows the average confidence on samples that were originally unlabeled, based on the model's highest predicted class probabilities. These values give a quick summary of compatibility, training setup, performance, and prediction certainty. The visualization first identifies which training samples were originally labeled, then plots all data points colored by their predicted labels. The original labeled seed points are emphasized with larger star markers and black edges, so they stand out from the propagated labels. The plot includes a title, axis labels for the two features, and a legend, making it easier to interpret the results of label propagation from the initial seeds. This script shows how label propagation can infer labels from very limited supervision. It creates two clusters, labels one sample in each cluster, and leaves the rest unlabeled. A k-nearest neighbors-based label propagation model spreads the known labels to nearby points, then evaluates accuracy and average confidence on the previously unlabeled data. A scatterplot highlights the original labeled seeds, and shows how the model assigned labels across the dataset. Label spreading. Label spreading is a semi-supervised learning method that uses a small set of labeled data and a larger set of unlabeled data. It connects similar samples in a graph, then spreads labels through that structure to infer likely labels for the unlabeled points. By using broader patterns such as clusters and regions of similarity, it works well when labels are limited but unlabeled data is plentiful. Label spreading is a more flexible version of label propagation because it does not treat the initial labels as completely fixed. It can adjust labels slightly when the graph shows a stronger pattern, which helps when some labels are noisy or wrong. By balancing the original label information with agreement among connected samples, label spreading is often more robust in noisy data. When evaluating label spreading, consider both prediction quality and how labels propagate through the graph. It works best when similar samples form clear clusters and decision boundaries fall in sparse regions, such as in news or product categorization. It can fail when dissimilar samples are strongly connected or one class spreads too widely. So check accuracy along with confidence, class balance, and whether uncertain samples lie near natural boundaries. Python code label spreading. This example shows label spreading when only a few samples are labeled. Labels are passed to nearby unlabeled points through graph smoothing, producing predictions that separate the data into two clusters. We import key Python libraries for the example: NumPy for numerical work, Matplotlib for visualization, and Scikit-Learn for machine learning tools. We also use Scikit-Learn's Moons dataset generator to create two interleaving half circles, which will serve as sample data for label spreading. We import three key tools from Scikit-Learn: a train test split function to divide data into training and testing sets, the label spreading algorithm to infer labels for unlabeled data using a few labeled examples, and an accuracy scoring function to compare predictions with true labels. Together, these tools support building and evaluating a semi-supervised learning model on unseen data. A two-class dataset is created using Scikit-Learn's makeMoons function. It generates 300 points shaped like two interleaving half circles, with a small amount of noise added for randomness. A fixed random state ensures the same data is produced each time, and the result includes the point coordinates and their true class labels. The dataset is split into training and testing sets using Scikit-Learn's train test split function. 35% of the data is kept for testing, giving a separate set for evaluating the model. Stratification preserves the class proportions in both sets, and a random state of 42 makes the split reproducible. We create a label array with the same shape as the training labels and mark its entries as -1 to indicate unlabeled samples. This hides most labels, so the label spreading process can infer the missing ones. To create a small labeled set for semi-supervised learning, we keep only a few known labels from each class. For both class 0 and class 1, we find matching training examples, choose the first 6, and mark them with their true class. These limited labeled samples provide guidance for the label spreading process. We count how many samples already have labels by excluding entries marked as unlabeled. This count is checked against the expected total of 12 labeled samples. If the number is wrong, an error is raised, so the label spreading process only continues when the correct labeled anchor points are in place. A label spreading model is set up with a radial basis function kernel to spread labels through the data graph. Its settings control how strongly nearby points influence each other, how much the model balances given labels with its predictions, and how long it can iterate toward convergence. The model is then trained on the feature data and semi-supervised labels, allowing it to infer labels for unlabeled points by smoothing information across the graph structure. The model is evaluated by making predictions on test data that was not used during training. Then, Scikit-Learn's accuracy score measures the share of predictions that match the true test labels, giving a simple estimate of how well the model performs on unseen data. Use the model's transduction result to get the predicted labels for the training data after label spreading. Then compare these predictions with the true training labels to compute accuracy, which shows how well the model recovered the original labels from partially labeled data. The output reports key checks and results for the label spreading experiment. It shows the Scikit-Learn version for reproducibility, the number of initially labeled training samples, the accuracy of recovered training labels, and the held-out test accuracy. Together, these values indicate how well the model learned from limited labeled data, and how well it generalizes to unseen data. We begin by creating a matplotlib figure and axis to visualize the label spreading model. This sets up a 7 by 5 inch plotting area, where the model's smooth learned regions and the initial labeled samples can be shown. A scatter plot is created using the first two training feature columns as the point coordinates. Each point is colored by the model's predicted label with a cool to warm color map, making the predicted classes easy to distinguish. We first identify the training samples that already have labels by selecting those whose semi-supervised label is not -1. These labeled points are then plotted using their feature coordinates with larger black outlines and no fill, so they stand out from unlabeled data. The plot is finalized by adding a title that notes label spreading was performed with 12 labeled samples. The axes are labeled as Feature 1 and Feature 2, a legend is placed automatically in the best location, and the plot is displayed to show the data and label spreading results. This script shows label spreading, a semi-supervised learning method, on two moon-shaped clusters. It hides most training labels, leaving only a few labeled examples from each class, then uses a radial basis function kernel to spread those labels through the unlabeled data. The model is tested on held-out samples and also checked on how well it recovered the hidden training labels. A visualization highlights the inferred label regions and the few original labeled points, showing how label spreading can learn useful structure from limited labeled data. Graph kernel choices. Graph-based labeling depends on how the graph is built, because the graph defines which samples are considered similar and how strongly labels can spread between them. A good graph kernel connects samples that truly belong together, allowing labels to propagate meaningfully. If the connections reflect noise or superficial features, labels may spread incorrectly. In this way, the kernel links raw data to the assumption that closely connected samples should share labels. Graph construction often uses either nearest neighbor methods or radial basis function kernels to define similarity. Nearest neighbor graphs preserve local structure by linking each sample to a small set of nearby samples. But choosing too few or too many neighbors can either disconnect the graph or blur boundaries. Radial basis function kernels create smoother distance-based connections, but their scale must be tuned carefully to avoid fragmentation or over-smoothing. The best choice depends on how the method should represent similarity and influence in the data. When using graph kernels, the graph should match the real structure of the problem, so labels spread within meaningful groups without crossing important boundaries. Good evaluation checks whether labeled data is well placed, boundary cases remain uncertain, and results are stable under small kernel changes. Label spreading is often more robust than strict propagation because it smooths errors, though it can weaken rare classes if the graph is unbalanced. Overall, graph kernels express assumptions about similarity and how information should flow through the data. Python code. Graph kernel choices. Graph kernels affect how labels spread in semi-supervised labeling. Comparing different kernels shows that each one can produce different decision regions, so the kernel choice is important for the final labeling result. This setup imports the main tools needed for a semi-supervised classification example. NumPy supports numerical arrays, Matplotlib creates visualizations, and the Scikit-Learn version helps with reproducibility. The Moons dataset generator creates a synthetic two-class dataset, while accuracy scoring evaluates model performance. Label spreading is used to propagate labels from limited labeled data, and standard scaling prepares the features for distance-based methods. A synthetic dataset is created with Scikit-Learn's makeMoons function, which produces two interleaving half circles for testing clustering methods. It generates 240 samples with a small amount of noise to make the data less perfectly separated, and a fixed random state ensures the same data is produced each time. The result includes the point coordinates and their true class labels. Before using distance-based graph kernels, the features are standardized, so each one contributes fairly. A standard scaling tool computes the needed values and transforms the data, so features have a mean of 0 and a standard deviation of 1. This prevents features with larger ranges from dominating distance calculations. A label array is first initialized, so every sample is marked as unknown. Then, for each of the two classes, only the first 4 matching samples are given their true class label. This leaves most samples unlabeled, creating a small labeled set for a semi-supervised learning setup. The process counts how many samples have known labels by ignoring entries marked as unknown. It then checks that the total is exactly 8, ensuring enough labeled examples for both classes in semi-supervised learning. If the count is different, an error is raised because the expected label data requirement has not been met. A label spreading model is built using a k-nearest neighbors graph, with 7 neighbors used to define how nearby points influence each other. The alpha setting of 0.2 balances the original labels with the labels learned during propagation. After fitting the model to the features and available labels, it spreads the known labels through the unlabeled data based on the nearest neighbor graph. A label spreading model is built with a radial basis function kernel to capture nonlinear relationships based on distances between data points. The gamma setting controls how strongly each point influences others, while alpha balances the original labels with the model's predictions. After fitting the model to the features and known labels, it spreads label information to estimate the missing labels. We evaluate each graph kernel by comparing the model's predicted labels with the true hidden labels. Accuracy is computed for both the k-nearest neighbor kernel and the radial basis function kernel. These scores show how effectively each kernel spreads labels in the semi-supervised task. The output reports the Scikit-Learn version for reproducibility, then shows how many samples were labeled for semi-supervised learning. It also compares the accuracy of 2 graph kernels, k-nearest neighbor and RBF, to evaluate how well each predicted the hidden labels. A new plotting canvas is created with a 7 by 5 inch figure. Then the data points are shown in a scatter plot using the first 2 feature columns as coordinates. Each point is colored according to the RBF model's predicted class, using a cool-warm color map to separate the classes visually. The points are moderately sized and slightly transparent, so overlapping areas are easier to see. To highlight the data points that were originally labeled, we first identify the entries whose labels are not -1. We then plot only those points using their 2 feature values as coordinates, coloring them by their true labels with a contrasting color map. Larger markers, black edges, and a clear label make these original labeled points stand out from the rest of the dataset. The plot is prepared to show label spreading using an RBF graph kernel. Its axes describe the 2 scaled features being visualized, and a legend is added automatically to identify the plotted categories. The visualization is then displayed for analysis. This script shows semi-supervised learning on a 2 Moons dataset using label spreading with 2 graph kernels, k-nearest neighbors and radial basis function. Only a small set of points starts with labels, while the rest are treated as unknown, and the features are scaled for fair distance comparisons. Both models predict the missing labels, and their accuracies are compared against the true labels. The script also visualizes the radial basis function decision regions and the originally labeled points to show how the kernel shapes label propagation. In this lecture, you learned to represent labeled and unlabeled samples for semi-supervised estimators, apply self-training with threshold and k-best pseudo-labeling strategies, and use graph-based label propagation and spreading methods and evaluate their behavior. In the next module, Module 20, we will go over feature selection.
Thank you for your attention. See you all in the next lecture.